looking at topic P9 Motion, and today we're looking at velocity and acceleration. So our expected outcomes for today, a grade 4 is if you could describe the difference between speed and velocity and use an appropriate example. A grade 5 is if you can identify the features of a velocity time graph, basically look at the graph and be able to describe what it tells you. And a grade 6 is if you can successfully calculate acceleration using an equation. So let's start off with this racetrack, and using this racetrack we're going to look at the idea of displacement, distance and velocity. So here we have a small racing car, there it is, and it travels around this 3-kilometer racetrack in 90 seconds. The first thing we need to do is to convert that 3 kilometers into meters, so that is of course 3,000 meters. 90 seconds stays the same. Its average speed will be 3,000 divided by the 90, which will give us 33.3 meters per second. So that's the average speed of the car. So second question, where is the car in relation to the start point? Well, it's on the start point. So how far away from the start point is it? 0 meters. But the car has travelled right around the track. So it's gone from here right the way around and it's returned to the start. But that was 3,000 meters. So this doesn't make sense. How can the car be 0 meters and 3,000 meters from the start point? Well, this is where we look at the idea of displacement being where the object is. The object is 0 meters away from the start point. Distance is how far it's travelled, and it's travelled from here all the way around and come back to the start point again. So it has in fact travelled 3,000 meters. So its displacement is 0 meters and its distance is 3,000 meters. So that's the difference between those two. Now its displacement depends on its velocity. Velocity is speed in a given direction. So if we look at our racetrack, the car is travelling in this direction initially, so it has a certain velocity. Then it gets to the corner and is changing direction. So the velocity is changing. The speed may be exactly the same. Here the velocity becomes constant again because it's travelling in the same direction. And then we get to this corner and the velocity is changing until we return to the start. So that's why our displacement can be 0 again, because the velocity basically changed, the object went round in a circle, returned to the start. Right, now we looked at one of these graphs in our last motion video. So this of course is a distance time graph. Distance given on the y-axis, time given on the x-axis. Now this line shows that the distance is increasing. Okay, the object is getting further and further away from 0 as time passes. So that's what we're seeing here. But it's not constant. We can see that the amount of distance is increasing consistently with time. So there's more and more distance. There's a greater and greater distance with every unit of time. So this is a graph showing acceleration. And hopefully you've remembered that from last time. Now, what is acceleration then? Well, to calculate acceleration, which is a rate of increase of speed, we use an equation. And the equation is quite straightforward. Acceleration is given by change in velocity, units, meters per second, divided by the time taken for that change to happen in seconds. So the other way we can also write this change in velocity can also be written as the final velocity v minus the initial velocity u. The final velocity is what you end up with. The initial velocity is what you started with. So this triangle shows us that in a bit more detail. And the interesting thing, we've now got a number of ideas about units for acceleration. acceleration can be given in meters per second squared. It can also be written as meters per second, or it can be written as ms to the minus 2. Any of those will be correct when you use them. Now we're going to look at an equation then, and we're going to do a calculation. So if we look at this question, a car takes 8 seconds to accelerate from rest to 28 meters per second. We need to calculate the average acceleration. So we always put the subjects of our equation down, and we need to think about whether we know them or not. Well, the acceleration, we don't know. That's what we're trying to find out. The change in velocity, yes, we do know that. We know that the final velocity, v, is 28 meters per second. We know the initial velocity, u, is 0. If an object is at rest, it means it's not moving, so that's 0 meters per second. And we do know the time. The time is 8 seconds. So the acceleration is going to be v minus u divided by t, which is going to be 28 minus 0 divided by 8. The acceleration is therefore change in velocity, which is going to be 28 divided by 8, which is going to be 3.5, and then we remember our units. I always like to do ms to the minus 2. Whoops, nearly forgot my decimal point. There we go. So there's an example of how we would do a calculation to determine the acceleration of an object. Next, we're going to take a look at a velocity time graph. Now, do not confuse this with a distance time graph. They're both showing very different things, and the lines are going to mean very different things. So always look carefully at the axes. The velocity of the object will plot the time on the x-axis and the speed or velocity on the y-axis. So this is a velocity time graph. So, as before, we can actually interpret this graph. So for example, in this little section from 0 to 10 here, this line, we can see that the speed is increasing. And because it's in a straight line, that tells us it's increasing constantly. So this little section here is constant acceleration. And from this graph, we can also calculate the acceleration. The change in velocity is going from 0 to 15. So that's going to be 15, change in velocity. And the time is 10 seconds. So from 0 to 10, 10 seconds. So 15 divided by 10 is 1.5 meters per second, or ms to the minus 2. If we look at this second section from time 10 to time 20, we see that the graph is flat. The speed is staying at 15 meters per second. Therefore, the acceleration is 0, and that means this object is traveling at a constant speed of 15 meters per second. Now, the next section we look at is from 20 seconds to 30 seconds. So again, that's a 10-second interval. And if we look at the speed, it's gone from 15 to 25. So that's an increase of 10 meters per second. Therefore, the acceleration, because again, we're seeing an increase in speed in a straight line, this time it's not as steep, so it should be less acceleration. And we can work it out if we do 10 meters per second change over 10 seconds, the acceleration is 1 meter per second. So it's accelerating but less than before. Final section then, we can see here that the line is now going from 25 to 0. So this is a deceleration. Or we also say negative acceleration. And again, we can see that the line is straight, so that's telling us that the deceleration is constant, and we can calculate that deceleration. So if we look back at it, our time is from 30 to 50, so that's taking us 20 seconds, and we've gone from 25 down to 0, so we've got a change in velocity of 25 meters per second. So 25 divided by 20 gives us 1.25 meters per second squared again. There we go. That's how we read a velocity time graph. So we can tell from the lines whether we've got acceleration, constant speed, acceleration, and this is deceleration or negative acceleration. Here we can see examples of those things again. So this is constant acceleration, this is constant acceleration, this would be a high acceleration, this would be a lower acceleration, this is constant velocity, speed remains the same, and this is constant deceleration or a negative acceleration. And the last thing we need to do is look at how we use a velocity time graph to calculate the distance travelled. And to do that, we need to find the area under the graph. So the part that's shaded, the green part, that's the area we're looking for, and whatever that is, that equates to the distance travelled. Now the way we do this, because of the shape of the graph, we basically separate the graph into different shapes that we can calculate the area of. So in this case we've got triangle 1, rectangle 1 and triangle 2. So if we look at triangle 1, we can see that the time is 4 and the speed is 6, so that's 4 and 6. The equation for the area of a triangle is a half the base times the height, so a half the 6 times 4. That'll give us an answer of 12. The rectangle, we can see it goes from 4 to 14, so that's 10, and 6 on that side. So we're adding that on. 6 times 10 is going to be 60. And this triangle is going from 14 to 16, so that's 2. Height of 6 again, so it's a half 6 times 2, so that's going to give us 6. And if we add a 12, 60 and 6, we get an answer of 78 meters. So that is the process we use to work out the distance travelled. We split the graph up into different geometric shapes, triangles and rectangles, calculate the area of each one, add them together. That gives us the total area, which is the distance. Well, that concludes this video. I hope it's been useful for you. Thank you very much.